Okay. Okay. So this is about the Core One project that Demitri and I started about 2 years ago. And we want to give you an update. We're ready to go live here in early 25. And that's what this presentation is about. A little bit about me is I work for a space company called Next Stage LLC, and I am the chief avionics architect. We are designing, I actually have already designed microchip polar fire space avionics computer, and just recently designed the combo I/O board, and we're going to be marketing this to people in the space community. My company has agreed to let us use the Core One project, so it's going to be warp speed going forward. My background is in electrical engineering, embedded, been a fourth programmer since '89, C programmer since 2000. I do mechatronics engineering. I've just had a company for 10 years where I designed the entire robot, and I've been doing FPGA since about 95. Demitri, do you want to talk about yourself, Demitri?
Yeah, so I work as a digital hardware verification engineer. I have a background in electronics engineering and software. Some of the things I've learned about are behavioral system Verilog, behavioral VHDL. These are paradigms that differ from traditional, which is where we focus on register to register, but rather it's like writing a program that can later get synthesized into the logic. So you think at a higher level. I've been working along the Core One in my spare time. Uh, I think I was introduced to Forth about four or 5 years ago, and some of my work has been working on a Prolog in Forth implementation, writing an expert system in Forth, and also porting the Meta 2 compiler in Forth, which I think was my very first talk I actually did. And so, as you can tell from this, I'm very interested in building new languages in Forth. However, I love Forth as it is. I like writing programs in it all the time, and the way I can just explore different technologies.
So Forth has a long history of being implemented in hardware. Goes way back into the mid '80s, where Chuck actually was developing ASICs 4000, NC 4000, for example, Shaboom, RTX 2000, F21, and then currently, they have a company called um, Green Arrays, and they have their GA 144. What we're working on is an FPGA version. Forth is really a virtual machine. It's Forth is really um, a hardware design. It really is. Um, Chuck mentioned he discovered Forth writing assembler code, and it was a kind of a funny story. He talked about he was writing assembler and he started using the stack and making calls and got the Forth concept, from writing assembler code. I thought that was a very interesting story. He's the inventor of Forth, but he said he discovered it because the reason is it's a very simple, powerful design for a computer in hardware, and he's built many Forth computers in hardware. Um, yeah, it's very easy to implement in hardware. So his talk last Forth Day, he said something that kind of hit me hard. He said, Forth, there really never has been a Forth 2.0 because Forth is, it's perfect the way it is. And Forth is so amazing in the ability to create, it's really a meta language to create other languages. And I just really thought that there should be a Forth 2.0, And we call it Forth 2.0 because we want heritage of Forth, but we also want to tell people that this is a newer version, more modern version, where it even supports, potentially infix notation as an example. So, Forth is very unique. It's an interpreter on a chip. We have implemented the outer interpreter and compiler inside the FPGA as a coprocessor to a Core 1 core. And what that means is the Core 1 core could be running your machine. At the same time, you could be downloading and compiling, interpreting and compiling new code. And then in a few clock cycles, you can switch to that new code, which is really important for space systems. I've asked many a space engineer, if you have 100 robots operating out at Pluto and you have to update all the software over a 750 character per second NASA Deep Space Link, how do you do that? I literally in the last year, I've been to four space shows. Not a soul has told me how to do that, because in C, if you change one line of code, you got this new binary blob. With Forth, you just upload the source code of the function you want to change, and it might take a second over, that'd be 750 characters. That's a lot for Forth. And we also developed the incremental compiler on chip. It's very easy to accelerate your software using hardware. It also supports massively parallel architectures. You can have hundreds or even thousands of parallel processes depending on the size of your FPGA. One of the things that I want to do going forward is to build an AI inference engine for LLMs. So Llama, for example, is open source. And you could use the Llama 7B, which would fit in local flash memory, and you could actually implement one of these chats on it inside of an embedded system, you might say. And one of the things we're really working on right now is we're really blurring hardware and software, the wall between them. Normally you have, hardware level, and then you have device drivers, and you have an operating system, then device drivers, and then applications. And our system, it's just because it's Forth, it's blurred. There's no operating system because we are Forth is the operating system. A lot more energy efficient. We can do real-time AI, and basically we'll embed OS functions in the Forth system on chip. So one of the new things that we've been working on, I call it smart tokens. Maybe one of you guys come up with a better name, but basically it's pretty cool. And I'm going to get to that screen in a minute. You can microcode Forth programs and words on chip in boot ROM. So imagine having dozens of cores operating simultaneously, and you put them in some sort of network talking to each other. And each one of these Core 1 cores would have its own small memory of any size. It could be 16-bit, 32-bit, it could be 47 bits, it doesn't matter. And you also, each one of these cores would have implemented a boot ROM that would run your code. And I'll show you some of that. So the Core 1 extensions can be complex. So for example, let's say you want an FFT opcode. Well, you can do that in our system because we basically stall the inner interpreter until an opcode completes. We have what we call a busy flag. So okay, as many cycles as you need to execute. So you can, create very complicated opcodes inside our system. Forth words can be coded as opcodes. So you could, write a Forth program and say, you know what, I'm spending too much time on this particular word, and you recode it in System Verilog, you make it an opcode. It'll run faster than than if it was in the fourth machine. Although the fourth machine runs real fast, nothing runs faster than a dedicated, circuit that has been coded in System Verilog. And custom opcodes, they execute at the speed of silicon. We can still borrow high-level concepts from other popular languages. Demitri, for example, has created Prolog in Forth in like 400 lines of Forth code, as an example. Pascal, even C. Oh, I like Struck in C, about the only thing I like in C. And you can borrow and steal these things, and we can implement these in Forth 2.0. We can network multiple cores together. They could be 16-bit, 32-bit, 64-bit, up to 256 bits on an FPGA. You can store source code in Flash or on disk, and you can compile it on the fly as needed. That's going to be a very interesting thing to work with later on. Massively parallel computer on a single chip. So think of the fourth computer is the conductor of an orchestra. An orchestra is a great analogy because you have, 50 musicians. They're all individual computers, right? But you have a conductor of that orchestra keeping everything in line and making sure that everything is timed perfectly. So I look at the fourth computer. You would probably, for most applications, only instantiate one of them, and because that's your user interface is the fourth two computer, and then it controls a lot of distributed Core 1 cores, throughout the system. As an example, put one on the display controller, one on the disk controller. So imagine the fourth computer says, disk controller Core 1, go find me all the files that have fourth in it. And so that Core 1 would run off, find all the files, and when it's finished, it would notify the fourth two computer that, hey, I've done it, here's your list. And the fourth two computer could be doing on other things while it's doing that. Same thing, you could have it as a network controller. I'm a big fan, instead of doing buses, I'd rather do networks and stars, or even think of an inverted tree. So the top trunk of the tree is the Forth 2.0 computer, and then you have all these branches that go down and talk to these different subsystems. So you don't have the bus bottleneck. So this is kind of an example. One of the things that's very unique is the interpreter compiler, which is running at 250 megahertz, is a separate process in our system. So it's not sequential. The Core 1 core is operating and running your system. The interpreter compiler is actually a separate computer on chip, and the two, interact with each other. So it's already a parallel machine. Now, underneath the Core 1 in this picture, I say parallel processing device drivers. So what that means is, you might have System Verilog code to run a display, one, talking to the disk controller, one talking to communications, that sort of thing. Well, you can use C with our system too. So what you do is you instantiate a RISC-V core. Now, remember, RISC-V cores, they need dedicated memory. So you're going to use, extra pins on the FPGA to hook up DDR4 and flash, and then you'd have a core, a RISC-V core system. And then you could, it could be a coprocessor. So let's just say you have a lot of code in C, and you want to just use it, use that as in your widget, in your product. Well, you can use the fourth computer as basically the controller of the whole system. And the fourth computer uses so little memory that we just use the memory inside the FPGA. We don't need any external memory whatsoever. So what about a massively parallel computer? Use the fourth computer, like I said, and this is a pictorial where you have the user that's talking to the fourth computer, and then it's managing massive parallel processing on an FPGA. So I've been working on this for a little bit. AI Playground Development Board. We're putting an ESP32 on it. Again, access the internet. I'm really excited about Brad's today because I want to use the ESP32 to talk to online like Gemini. He's got a Gemini port going on, so I'm really going to use his stuff there. I'm changing the concept of it. I used to have high-speed SRAM. The high-speed SRAM was 4 times slower than an FPGA, so I ditched the SRAM and I put the money to the FPGA, and now we're using an FPGA with 112,000 LUTs. To give you an example, the fourth computer, with integrated core one is only 3,000 LUTs. So you could put 30 of them, you could put 30 full fourth computers on a chip. I don't know what you'd do with that, but you could put, maybe one fourth computer and 60 to 100 cores on there. It's going to have Arduino Shield compatible connectors, high-speed SerDes, PS2 keyboard, a 4.5-inch 480 by 320 color display. It's going to have, I'm looking at putting an SSD chip on there instead of flash. It's going to have either flash or the SSD, and it will have an SD card. And that's a picture of the board. So I have 2 groups I've started, AI and Robotics on Facebook, and I also have AI Robotics Group on LinkedIn. Between the two, there's about 4,000 members. And we talk about a lot about AI and robotics. That's my thing. And I'm going to be using the Core 1 and the fourth 2.0 computer in AI and robotics. That's what I always wanted it for. So as an example, in the terminal, you could, because we have a terminal, right, talking to fourth. You could just say the keyword chat, tell me about AI and robotics, and then it comes back. It goes out to the ESP32, and it talks to the AI, and it parses, it captures back all the text, and then it displays it on your screen. So I got a little note for you, Brad, down there. So advanced parsing. So this is why we're calling it Forth 2.0. So at the top, you have, you're defining add, multiply, right? And then you have immediate words, local X, local Y, and you can use infix here. We can, because our parser is so powerful, it's running at a clock speed at 250 megahertz. It can do all kinds of processing, on the source and do some really complex stuff in a fraction of a second. So you can have locals. You could comes down and you say result. Well, the parser compiler could say, oh, I don't have a word called result. I'm going to create a variable called result, and then the function is going to be equal, and it parses this, and it actually, when you hit the semicolon, it will forget the local variables that were created in the dictionary, and but it will have when it executes, it'll create the result. Versus the bottom is how you do it in Forth, right? And I'm a Forth programmer, so I know what that means. But if you're not a Forth programmer, what does that mean? Wrote plus times result store. You have to learn Forth. So our concept is, and by the way, if somebody asked me, they got a little excited. They said, "Oh, you're going to get rid of Forth?" No, we will always support Forth 1.0 dupe, swap, drop, create, does. All the base words will always be in our system. If you want to write pure forth, go ahead. But we want to expand our market to everybody else. So this is an example of primitive forth words in system Verilog. Really complicated. Look at that. Minus. It's one line of code. Top of data stack. Demitri did make top of data stack a register. That's why it doesn't show a stack word. But you can see at the end it says minus data stack DP. So that's actually accessing the stack. And so minus is one line of code. One plus is one line of code. Everybody in the audience, you're a programmer, you can read this. This is this is easy stuff, even though it's system Verilog, which was modeled after C. So if you look it over, there's two lines of code. So it's very, very easy for you to add your own opcodes to our system. This has got me really excited. So in system Verilog, like C, they have type def. So instead of the base system is a 32 bits, a 32-bit. We're going to make it more complicated here, but it's gonna make the system more powerful. So basic, and I think Chuck, correct me if I'm wrong. In color forth, you use the upper bits to denote colors and different functionality in color forth, and I think that's a fantastic idea. So that's what this does. You can create and you can actually change this. You can add your own bits or your own records, you might say. So you notice that in our system, we have to know whether it's a CFA or a token, because if it's an opcode, a token, we process it differently than if it's a CFA. If the user created it and it's in the dictionary, we have to process it differently than if it's a token. So we have to know that. And then if you have an immediate word, you just set a bit, and now the system knows that you want to execute. That's a CFA to execute. In forth, we have to compile lit and then the number. That's two operations. So we have a number bit. So that bit is set, and now it tells the system that the 32-bit data is actually a number, and it just will put it on the stack. My favorite one is called type. So 3 to 0 means that there's 4 bits, so you have 16 different types. Now, this type could be a pointer to a list. It could be a string pointer. It could be an array pointer, list. It could be a pointer to a list of pointers. All right. Really powerful stuff. And then the last line there, the data size is in our system. It's one parameter that you change. You can change, and so just read that that's a 32-bit data. So you have 32 bits of data, and because it's an FPGA, you can't do this in a micro. It's very difficult because it has a fixed data width size. So you'd have to take away from the data to implement this. So if you had a 32-bit wide system, maybe numbers and stuff could only be 26 bits, right? But on FPGA, we can go to 32-bit. So on the bottom there, use a parameter. And so we're naming number mask as, the first bit is that, immediate mask, second bit is set. And that's how you do it in System Verilog. So you guys are learning a little System Verilog here. Not hard, right? Okay, Demitri, you're up.
Great. So what I really want to discuss here is language versus technology. And you're going to see exactly what I mean and how that relates to fourth. So, I mean, we have here a list of 12, I think, of the most popular languages and how difficult they're considered to be. Now, discussions about languages and which one people prefer tend to tend to reduce themselves to conversations about syntax, very superficial things, sometimes the community, where it's used, and so on. But I noticed that there is not a lot of conversation about technology anymore, especially after development of all the paradigms. Next slide, Don. So yeah, we've seen it, Pascal versus C, C++ versus Java, Lisp versus Prolog. And again, a lot of the time they could do more or less the same things, have the same functionalities, but they had what slightly different approaches, more memory safety or less, and just look different. I mean, if you consider Lisp Prolog, you can implement Lisp in Prolog and you can implement Prolog in Lisp. So they can actually really be easily implemented in each other, but there was actually quite a division on that part. But what about the technologies? What kind of technologies are in these languages? And what's the technology in fourth? Well, I think fourth has the best technology, especially when we combine it with FPGA. I'll show you why on the next slide. So what are the core technologies of fourth? Well, first one is to be able to interact and get immediate feedback. You can run pieces of code interactively, which helps with testing. It helps with debugging. It's one of the key parts of fourth. And this is normal for how we work, but you have to remember that this is actually not normal in other languages like C++. So benefit from incremental compilation. We can add one new word to the system and have that compiled without recompiling the whole program. You won't believe how long it takes to compile an entire C++ program or something of the like, just for a small change. And then if you have a micro, you're then having to upload all of that code again, especially as Don mentioned with the satellites. Another thing as well is the memory efficiency of fourth. And I was debating at first whether to put this in memory efficiency. Is that relevant? But it definitely is relevant, especially when it comes to FPGA, because when you can use memory efficiently, there's more things that you're able to do. For example, you can use memory that's available on the FPGA chip itself without having to go to an external memory. And I will tell you that in CPU design, having to go to an external memory is actually one of the big challenges. When you get those cache misses, you're introducing hundreds of cycles of delay for the instruction. And that often happens at like every time a new function is called. Next slide. So what about readability when it comes to Don? I think you've got the wrong slide here. I'll let Don pull it up. But meanwhile, while he brings up the right slide, I'll explain. Fourth, so we're all familiar with fourth. We understand RPN. It doesn't scare us, and it doesn't scare me especially. But we understand that readability is one of the barriers that comes up when it comes to fourth. And on the core one, we want to address this directly by really focusing on infix notation. Infix notation is more familiar to most programmers. It makes the structure of expressions clearer and often easier to read. And here's the thing, with an FPGA handling infix parsing, we actually can retain efficiency of and performance of fourth, but gain readability. So we have plans to accelerate that. Don, maybe is it worth me taking over and sharing? Right, here we go. Right, so yes, these are the main core fourth technologies. I think if I do slideshow, is that visible? Yeah, that's visible to everyone. Perfect. So yeah, also rapid virtual machine and language creation. That's another thing. So you saw before how I've worked on porting different languages to fourth. So I think part of that is being able to create virtual machines easily. So as I mentioned about FPGAs and infix. I'll explain about that on the next slide. The other thing is local variables. You can reduce stack juggling. You can simplify complex expression, especially if you're dealing with maths problems. And you can also enhance readability with clear variable names. So if you have a name of a variable in expression rather than just swap or wrote or whatever, then that does help, especially those who are less familiar with refactoring. So in our system, parse and compile, as well as execution, they happen in parallel at the hardware level. So we're not dealing with a very traditional case. We can have execution happening while we're parsing new code. And so we don't slow down our execution by having additional parsing. So what we are thinking is to make each keyword of a language a token or a fourth word. For example, I asked myself one time, why can't something like x equals y plus 2 be considered valid code? Just putting that question to myself on a system. Why can't that be valid on our system? Because if it was, then we could have an interactive, incrementally compiled C or Pascal-like language. Now, we're all here, we're fourth programmers, okay, but this would be for the C addicts. They can come in and they can benefit from that. And that would revolutionize programming for them because they don't have that facility at the moment. So how can some of these things be done? Well, I gave two examples here, something like Prolog. So Prolog is a logic programming language, and it relies a lot on backtracking and recursion. With backtracking, for example, you need a stack. You need to remember where to backtrack to. You also need stacks for the logic that you're evaluating. And Prolog actually has a lot of data structures, and that's one of the interesting things about it. So Prolog is really easy to implement it in itself because you can express the program in the Prolog language as structures and have logical rules operating on those structures. So that is something you can implement in FPGA hardware. On the other hand, if you had something like Pascal structured programming language, as I said, you make each token into a CFA. Like, so I can almost imagine it compiling from like left to right. That's one way. And each of those could actually be a CFA. It means that each word would have to do more than it traditionally does. So for example, a number might not just put a number on the stack, but maybe it checks some flags too to see where the number should go or if there's an operation being applied. This would not be feasible normally because it would require actual registers in memory and stuff. And when you access them, it's going to slow down the system. And of course, it would be impractical. But on FPGA, that is a completely different story. And so we can use registers, flags, stacks, wherever we need them for infix parsing. I made a reference here to the shunting yard algorithm, which I believe is the process to go from infix to postfix notation. So we could be doing that at the parsing level. So taking that infix code and turning it into postfix and then compiling it that way. But we could be doing it at runtime as well with the help of these data structures, which would simplify the compiling process. This is something that we'd like to run tests on and find out which one is the most beneficial in practice. About that word. So the advantage of this is the hardware. So the way we think of things is we have a word which maps to an opcode, and then that maps to a hardware driver. So there's a very clear path from word to driver, and we're trying to implement drivers in hardware, this FPGA, rather than doing it in software, because all these drivers can be running in parallel. So you can pretty much use Forth just as a controller. This allows us to create a truly responsive system without having an operating system layer. You consider, for example, with RISC-V, what typically happens. You have a RISC-V CPU, and then you work on trying to get C to compile to it. And then once you get C compiling, people trying to boot up into Linux. In top of Linux, there's going to be some libraries or application layers, and then you have the actual program you want to run. No. We want to change this paradigm and execute commands in real time with minimal latency. And this is key for real-time systems. For example, with satellites, this is a key thing. And also being able to update your programs too. If you've got lots of satellites away, you don't want to have to go through all of those stacks of software. So what this means is we're no longer writing software that interprets language. We're creating direct command pathways. And I think that is possibly the most Forth thing that we can be saying right now. A direct path to the hardware. It's what it's all been about since day one. So what is the yes? Well, there's a lot of discussions about language, a lot of arguments, a lot of disagreements. But really, if we think at the level of technology, that's the level we need to be thinking about. That's the real issue. And I will say something right now, which is, if you challenge us on the support for infix notation, bearing in mind that we will have support for RPN as well, you might be caught in this syntax trap as well. Because the only difference there is syntax. But the technology we want is that incremental compilation, is to be able to run whatever you like as directly as possible. When we argue about syntax, I put this, it's like arguing about the paint color for a house without a roof. Imagine that you have a house and you think, what color should this wall be? Well, no, it should be red. No, it should be green. No, it should be blue. Hey, there's no roof above. There's no roof. We are way behind on where we should be, I think, in terms of technology and how we're using it. So let's bring up the technology. And that means embracing Forth, because it's given us the greatest foundation technology-wise. Interactivity, incremental compilation, and memory efficiency. These things are powerful and enable us to act differently. This memory efficiency as well, I will reiterate, we can have programs running in from that is on the FPGA itself, not external in any way, and running at the speed of Fabric. It allows things that previously were not possible. It's one of the things that we want to preserve, as well as, again, interactive and incremental compilation. Things we take for granted but aren't appreciated and used by others in the programming world. We want them to benefit from the power of this too, without having to be caught up with things like stack juggling. That's why we have infix notation. And we believe that promotes Forth technology for modern programmers. That's it, nothing more needs to be said. Core 1 doesn't just interpret commands, it hosts languages natively by directly mapping their functionality to hardware. This is the future, native language hosting and having a really clear path from that language to the hardware. We want to completely bypass the idea of operating systems and allow people to interact with hardware the way that we do as Forth programmers, but enable them to do that as well with languages that maybe are of their choosing or have certain features that work well for the application. We believe that this is where thinking Forth was going. And being able to have languages that you implement on top of the structure of Forth, able to write an application that is specific for the problem that you're trying to solve. Don, I'll go back to you.
Yeah, I think this is a great stopping point. If we have any questions, how many minutes left do we have? Okay, is there any questions?
You got about 5 minutes.
guess I had a question, which is so for example, Prolog is inherently more parallel than maybe Lisp or maybe even a Forth. But with Forth, you're limited to a stack, so everything is going serial. In theory, with C, you could go parallel in the same way that Prolog does. So if you had a long expression in C, in theory, with infix notation, you could parallelize it. If you have a stack, maybe you can't parallelize it. But since you know Prolog, and Prolog is highly parallel, right? Because you could do multiple queries at once. I don't know what mechanism you need to go from a stack to make things more parallel. Once you have two queries like in Prolog instead of one, or multiple queries, they can all go in parallel. So and then maybe it's true for the expressions as well.
That's a really good point. So yeah, making expressions parallel and computing different parts of it. I think this could be possible. I would say that's less where our focus is, because when we think of being parallel, we're thinking more in terms of robotics and having different things that we're controlling. That doesn't mean that this couldn't be done if we noticed that there was a performance, notable performance thing when it came to, say, for example, we want to operate on arrays as well. That's one of the things, like sort of vector operations. So those might be slow, but if you could have like two vector operations running in parallel, which one, you kick off one job, it runs, you kick off another job, it runs, and you can have registers that tell you when they're finished. Maybe then you can read from these registers, and then you have your result. You can just kind of delegate that to a system and have it run it, and then come back to the result later. So there's many different paths you can go. I think for us, it's more to do with how we interact with other pieces of hardware. But if it made sense, we could port it to parsing expression parallel, including in Prolog.
So C actually runs on a sequential machine. You basically are simulating, it's multitasking, not multiprocessing, whereas an FPGA is truly multiprocessing. And they could either be written in straight system Verilog, and you could have hundreds or even thousands of parallel processes on an FPGA, or they could be, a core one cores. You could have multiple ones of those to implement your parallelism.
Okay, thank you, Don and Demitri. We really appreciate it. One note for the speakers. You have the schedule presumably in front of you. If not, go to MeetUp. It's there. That's the current schedule. It was updated a couple of times. So speakers, you got one that might have been a little off from actual reality. So the current real schedule is on MeetUp. In the room at Stanford, the one that Dave printed out is wrong. We're going to do the screenshot now. So if you are on the LAN or otherwise don't want your picture on the website, go to unpicture or log out. You can log back in a couple of minutes. You'll be safe then. If your camera's off and you want to be in the screenshot, turn your camera on. And we'll be pleased to add you to our rogues gallery. The Stanford folks will take a group photo later on. But if your picture is on the system, you're going to be on the website. So this is the time. You want to give us a countdown, Brad? Or?
It's always a little fickle, so
it's non-deterministic.
Smile real. So I'll say I'm going to start roughly now, and
I'd like to take this time to say, Brad, we're so grateful to you for managing the Zoomy stuff and the YouTubey stuff. Dave, we're so grateful to you for managing the Webby stuff. And we're all very grateful to all of you for coming to Fourth Day. And that concludes the screenshot portion of the program. It's safe to turn your camera back on, those of you that are trying to time out the statute of limitations or something. You have to be in the jurisdiction for which your crime is charged. Otherwise, the stop clock effect takes place. The clock stops on your statute of limitations. So please be aware of that. It's 10:37 and I'm not punctual. What else is? So Ed, it's you. Introduce yourself and tell us your stuff.
Okay, can you hear me?
We can hear you now.
Okay, I'm getting over a cold, so I may have to mute myself and pause and make some really awful noises and then unmute again. So bear with me. Well, actually, it's not a bear, it's a raccoon. Let me get my screen up. Okay, let me do a screen share here. That would be this guy. And I want that one.